Imagine the sound of the universe itself trembling, a ripple in the fabric of space and time so powerful it distorts reality. That's the haunting whisper of two black holes colliding, an event so cataclysmic it sends gravitational waves racing across the cosmos at the speed of light. These waves aren't just cosmic echoes, they're messages from the most violent and mysterious events in the universe, carrying secrets about how black holes merge, how stars explode, and even how the very fabric of space-time behaves. And the most incredible part, for billions of years we had no way to hear them until now. Gravitational waves are one of the most thrilling discoveries in modern astrophysics, a window into the hidden forces shaping our universe. Predicted by Einstein over a century ago but only directly detected in 2015, these ripples are like the universe's own Morse code, revealing events so distant and ancient they're almost beyond comprehension. Think about it: every time scientists detect a gravitational wave, they're essentially listening to the echoes of cosmic collisions that happened millions, even billions of years ago. It's time travel in the purest sense, a way to peer into the past and uncover the universe's best-kept secrets, and that's exactly what we're diving into today. Over the next 30 groundbreaking discoveries, we'll explore how gravitational waves have revolutionized our understanding of everything from black holes to the origins of the universe itself. You'll learn how these faint ripples in spacetime have led to jaw-dropping revelations, like the existence of black holes with masses we never thought possible, or the way spacetime can stretch and squeeze like an invisible ocean. This isn't just science, it's a detective story on a cosmic scale, and you're about to witness the most astonishing clues uncovered so far. So buckle up, because what you're about to discover will change the way you see the universe forever. The first direct detection of gravitational waves in 2015 wasn't just a scientific breakthrough, it was a moment that rewrote our understanding of the cosmos. After decades of searching, the Laser Interferometer Gravitational Wave Observatory, or LIGO, finally captured the faint, telltale ripple from a pair of black holes colliding over 1 billion light-years away. Picture this: two cosmic giants, each around 30 times the mass of our Sun, spiraling toward each other at nearly the speed of light before merging into a single, even more massive black hole. The energy released in that final moment was so immense, it warped spacetime itself, sending vibrations across the universe like a stone dropped into a pond. What made this detection so monumental? For starters, it proved Einstein right again. His theory of general relativity predicted gravitational waves back in 1915, but even he doubted we'd ever detect something so subtle. These waves stretch and compress space by a distance smaller than the width of an atomic nucleus, making them nearly impossible to measure. That's where LIGO genius comes in. Twin observatories in Louisiana and Washington, separated by thousands of miles, use lasers traveling down 4-kilometer-long vacuum tunnels to detect infinitesimal changes in spacetime. When the gravitational wave passed Earth, it altered the laser beam's paths by less than 1,000th the diameter of a proton, yet LIGO caught it. This discovery didn't just confirm a century-old hypothesis, it launched an entirely new way to explore the universe. Before 2015, astronomers relied on light, visible X-ray radio to study the cosmos. Now we could listen to spacetime itself. Those first gravitational waves revealed black holes merging, something invisible to traditional telescopes. Suddenly, we had proof that these dark behemoths not only exist but collide in the void, reshaping our understanding of how galaxies evolve. It was like switching from silent movies to surround sound, revealing a universe far more dynamic and violent than we'd ever imagined. And the implications keep growing. That single detection opened the floodgates. Since 2015, LIGO and its European counterpart, Virgo, have spotted dozens of mergers from black holes to neutron stars. Each event peels back another layer of cosmic mystery, showing us a universe teeming with unseen collisions and cataclysms. But perhaps the most profound takeaway is this: we're no longer just observers of the cosmos. We're now tuning into its vibrations, learning its language, one gravitational ripple at a time. Just 2 years after that first gravitational wave detection, the universe handed scientists another cosmic gift, one that would change astronomy forever. In August 2017, LIGO and Virgo caught something unprecedented: the ripples from 2 neutron stars colliding 130 million light-years away. But this time, something extraordinary happened. Unlike black hole mergers, which are invisible, this cosmic crash lit up the sky. For the first time in history, we detected both gravitational waves and light from the same event, a dazzling fireworks show of gamma rays, X-rays, and even visible light. It was like the universe had suddenly turned on subtitles, giving us a front-row seat to one of its most spectacular performances. Neutron stars are the dense remnants of exploded stars, city-sized objects so packed with matter, a single teaspoon would weigh 1 billion tons. When these 2 ultra-dense objects spiraled together, they didn't just warp space-time. They triggered an explosion so bright 70 observatories across Earth and space scrambled to watch. The aftermath was a cosmic goldmine, literally. The collision forged an entire ocean of heavy elements, including gold, platinum, and uranium, flinging them into space at nearly light speed. Suddenly, we had proof that the gold in your jewelry or the uranium in nuclear reactors wasn't just made in supernova, it was forged in the heart of neutron star collisions. But the real game-changer was what this event revealed about gamma-ray bursts, the universe's most energetic explosions. For decades, scientists debated their origins. Some thought they came from supernova, others suspected neutron star mergers. That 17 detection settled it. Within seconds of the gravitational wave arrival, a Fermi satellite spotted a gamma-ray burst from the same direction. It was the smoking gun. Short gamma-ray bursts do come from neutron stars crashing. This one observation tied together 3 cosmic mysteries: gravitational waves, gamma rays, and heavy elements like pieces of a puzzle we didn't even know fit. What makes this discovery so groundbreaking is how it transformed astronomy into a multi-messenger science. Before 2017, we studied the universe through light alone. Now we combine gravitational waves with electromagnetic signals, creating a richer, more immersive picture of cosmic events. It's the difference between watching a silent film and experiencing a movie in IMAX with surround sound. Every neutron star collision we detect now isn't just a blip in the data. It's a full sensory experience, revealing how matter behaves under extreme gravity, how elements spread through galaxies, and how the universe stitches itself together in the most violent ways imaginable. And the implications keep growing. Since that first detection, we've realized neutron star mergers might be the universe's primary factories for heavy elements, meaning the atoms that make up our planet, and even our bodies, might owe their existence to these cataclysmic crashes. Every time we detect another one, we're glimpsing the cosmic alchemy that built everything around us. So the next time you look at a gold ring or a starry sky, remember, you're witnessing the aftermath of a neutron star collision that happened billions of years ago. A violent, beautiful event that we can now finally see, hear, and understand. If you thought black holes were rare cosmic loners, think again. The flood of gravitational wave detections since 2015 has revealed something astonishing: black holes collide far more often than anyone predicted. Before LIGO, astronomers estimated maybe a few mergers per cubic gigaparsec of space per year. The reality, these dark giants are crashing into each other at rates that would make bumper cars look tame. Some calculations now suggest a black hole merger happens somewhere in the observable universe every 15 minutes. That's not just surprising, it's rewriting our understanding of how galaxies grow and evolve. So where are all these merging black holes coming from? The leading theory points to dense stellar nurseries, regions where massive stars are born, live fast, and die young. When these heavyweight stars collapse, they leave behind black holes that can eventually find each other in the cosmic crowd. But here's the twist: many of the black holes spotted via gravitational waves are far heavier than expected, some clocking in at 50, even 80 times the mass of our Sun. That defies older models of stellar evolution, which suggested stars that big should explode without leaving a black hole behind. Now, scientists are scrambling to explain how these unexpected heavyweights form and how they keep finding partners so easily. The implications stretch beyond just black holes themselves. Every merger pumps insane amounts of energy into space-time, potentially influencing how galaxies grow around them. Picture a cosmic domino effect. When two black holes merge, the recoil can kick the resulting larger black hole clear out of its host galaxy. Others might sink to the center, merging again and again to form the supermassive black holes we see anchoring galaxies today. This could explain why nearly every large galaxy we observe has a monstrous black hole at its heart. They've been growing through a diet of smaller mergers all along. But the biggest mystery remains how these black hole pairs get so close in the first place. Some could form from binary stars that collapse in tandem, but others might find each other later in chaotic star clusters, where gravitational encounters act like a cosmic matchmaking service. There's even a wilder possibility that some of these black holes were born in the early universe, long before galaxies as we know them existed. Every new gravitational wave detection adds another piece to the puzzle, revealing a universe far more dynamic and collision-prone than we ever imagined. What's clear is this: black holes aren't the solitary traps of light we once thought. They're social creatures drawn together in a cosmic dance that shapes the very structure of the universe around them. And with every merger detected, we're not just hearing the echoes of distant collisions. We're decoding the hidden rhythm of the cosmos itself. For decades, black holes seem to come in just two sizes: stellar mass black holes, weighing a few times our Sun's mass, and supermassive ones, millions or even billions of times heavier. But what about the middle ground? Astronomers long suspected the existence of intermediate mass black holes, cosmic middleweights between 1,000 and 100,000 solar masses. These elusive objects were the missing link in black hole evolution, theorized to be the seeds that grew into the supermassive giants at galaxy centers. Yet for years, evidence was scarce, leaving scientists divided. Some argued they didn't exist at all. Then gravitational waves handed us the smoking gun. In 2019, LIGO and Virgo detected something extraordinary: a gravitational wave signal from a collision involving a black hole roughly 140 times the mass of our Sun. This wasn't just another stellar mass merger. It was the first clear evidence of an intermediate mass black hole in action. The event was mind-bending. One black hole weighed in at 66 solar masses, already unusually hefty, but its partner was nearly twice as massive, a size that defied traditional stellar collapse models. When they merged, they created a final black hole of 142 solar masses, solidly in the intermediate range. Suddenly, the debate was over. These cosmic middleweights weren't just theoretical, they were real, and they were merging. Why had these objects been so hard to find? Unlike supermassive black holes, which announce their presence by devouring gas and glowing brightly, intermediate mass black holes are notoriously shy. Too large to form from a single collapsing star, yet too small to dominate a galaxy's center, they often lurk undetected in dense star clusters or dwarf galaxies. Traditional telescopes struggle to spot them unless they're actively feeding, which is rare. Gravitational waves change the game. By sensing their collisions, we bypass the need for light altogether, uncovering these hidden giants through the ripples they create in spacetime. The discovery opened a new chapter in black hole science. Intermediate mass black holes could be the cosmic glue that explains how supermassive black holes grew so big so fast in the early universe. Picture this: in the chaotic environment of young galaxies, these middleweights could have merged repeatedly, gobbling up smaller black holes and gas to balloon into the monsters we see today. Some might even be primordial, born not from stars but from the dense soup of the early universe itself. Every new detection peels back another layer, revealing a cosmos far more complex and dynamic than we ever imagined. Now, with each gravitational wave signal, we're not just filling in gaps, we're rewriting the story of how black holes shape the universe. And somewhere out there, hidden in the dark, countless more of these cosmic middleweights are waiting to be found. Scientists thought they had black holes figured out until gravitational waves showed them just how wrong they were. For years, our models predicted that dying stars could only collapse into black holes up to about 40 times the mass of our Sun. Anything heavier, according to theory, should vaporize itself in a catastrophic explosion called a pair instability supernova, leaving nothing behind. But when LIGO and Virgo started listening to the cosmos, they heard something impossible: black holes weighing 50, 60, even 80 solar masses, casually merging as if the laws of physics had taken a day off. These weren't just outliers, they were cosmic rule breakers, forcing astrophysicists back to the drawing board. So how does a star defy its own death sentence and form such a massive black hole? One possibility is that these heavyweights are actually second-generation black holes, the products of earlier mergers. Picture two smaller black holes colliding in a dense star cluster, their combined mass creating a new object too big to form from a single star. But that doesn't explain everything. Some of the detected black holes have spins that suggest they formed directly from collapsing stars, not from previous mergers. That leaves an even wilder scenario. Maybe our understanding of pair instability supernova is incomplete. Under certain extreme conditions like rapid rotation or unusual chemical composition, a massive star might just cheat death, collapsing straight into a black hole without the usual fireworks. The implications ripple far beyond black hole formation. If stars can produce black holes this heavy, it changes how we model the life cycles of the universe's earliest stars, which were far more massive than anything we see today. Those primordial giants could have sown the seeds for the supermassive black holes we now find at galaxy centers, growing faster and earlier than we ever thought possible. Every unexpected detection adds another twist to the story, revealing a universe that's far more creative and far less predictable than our textbooks suggested. Yet the biggest surprise might be how common these heavyweight black holes are. Early gravitational wave data hinted they were rare, but as detections piled up, a pattern emerged. The universe seems to produce them with alarming ease. Some regions of space might act like black hole factories, churning out these cosmic anomalies under conditions we're only beginning to understand. And with each new merger detected, one thing becomes clearer. The cosmos has a flair for the dramatic, bending the rules when we least expect it. What's thrilling is that we're not just observing these mysteries from a distance. Gravitational waves let us interrogate them directly, measuring masses and spins with precision to test every wild theory. Maybe the answer lies in undiscovered physics, or perhaps the universe just has a sense of humor, hiding its most massive creations in plain sight. Either way, one thing's certain: the era of gravitational wave astronomy is turning black hole science upside down, one impossible collision at a time. When neutron stars collide, they don't just create gravitational waves, they scream secrets about the very fabric of matter itself. These ultra-dense remnants of dead stars, packing more mass than our Sun into a sphere the size of a city, push the limits of physics to the breaking point. And when two of them spiral toward each other, the gravitational waves they emit carry an imprint of their most extreme and hidden properties, especially how they stretch and deform under each other's crushing gravity. This phenomenon, called tidal deformation, is like listening to the universe's most intense stress test, revealing what happens to matter squeezed beyond anything we can recreate on Earth. Here's why this matters. A neutron star's surface gravity is so strong, it warps space-time into a nearly inescapable prison. But as two neutron stars orbit each other, their mutual gravitational pull stretches them like cosmic taffy, creating bulges that ripple outward. The degree of this deformation depends on the star's internal structure, how stiff or squishy its nuclear matter is under unimaginable pressure. Gravitational waves capture this distortion with precision, acting as a universal ultrasound probing the star's deepest layers. The stiffer the star, the more it resists deformation, producing subtle differences in the wave pattern. Softer interiors, on the other hand, distort more dramatically, altering the signal in ways scientists can decode. The data from the 2017 neutron-star merger was a goldmine for this research. By analyzing the gravitational waves in the final moments before collision, physicists could measure how much the stars stretched, and the answer was startling. The observations suggested neutron star matter is surprisingly resistant to compression, more like a rigid spring than a gooey fluid. This ruled out some exotic theories predicting ultra-soft interiors where quarks float freely in a soup-like state. Instead, it pointed to a complex, layered structure, a crust of iron nuclei floating on a sea of superfluid neutrons with a core so dense, protons and neutrons might break apart into stranger particles we've yet to understand fully. What's even more mind-bending is how this ties into the fundamental forces of nature. At nuclear densities, the strong force, which usually binds atomic nuclei, starts battling gravity in ways we can't replicate in any lab. Neutron stars are essentially gigantic atomic nuclei held together by gravity, making them the ultimate testing ground for quantum chromodynamics, the theory governing how quarks and gluons interact. Every gravitational wave from a merger refines our models, telling us whether matter at these extremes behaves as predicted or if new physics is at play. Some theories suggest the cores might harbor hyperons, strange matter, or even free quarks, states so exotic they'd rewrite our understanding of particle physics. But the real breakthrough came when scientists combined gravitational wave data with electromagnetic observations from the same event. The afterglow of the 2017 collision helped constrain the star's sizes and masses independently, cross-checking the tidal deformation measurements. This multi-messenger approach revealed a consistency in the data, reinforcing that neutron stars likely have radii around 11 to 13 kilometers, a critical clue for understanding their internal composition. Suddenly, we weren't just guessing. We had hard numbers to plug into equations, narrowing down centuries of speculation into testable science. The implications stretch far beyond neutron stars themselves. These cosmic laboratories teach us about matter in conditions so extreme. They mimic the universe's first microseconds after the Big Bang or the speculative interiors of quark stars. Every merger detected adds another piece to the puzzle, helping us answer one of physics' biggest questions: what happens to matter when you crush it beyond recognition? Gravitational waves aren't just cosmic messengers, they're the keys to unlocking the universe's most guarded secrets, one cataclysmic collision at a time. Einstein's theory of general relativity made a bold claim: gravity doesn't act instantaneously across the universe. Instead, it ripples through space-time at a very specific speed, the speed of light. For over a century, this prediction stood as one of the most profound yet untested pillars of his theory. Then came gravitational wave astronomy, offering scientists the perfect cosmic stopwatch to finally put it to the test. When LIGO detected its first black hole collision in 2015, physicists realized they weren't just witnessing a distant cataclysm. They were holding the key to measuring gravity's speed with unprecedented precision. Here's how it works. Gravitational waves and light, though fundamentally different, both travel as vibrations in spacetime at the same universal speed limit. If gravity moved faster or slower than light, it would violate relativity's core principles and force us to rewrite the laws of physics. But proving this required a rare cosmic coincidence, an event violent enough to produce both gravitational waves and light, so we could compare their arrival times. For decades, this seemed nearly impossible. Then, in 2017, the universe delivered the perfect experiment, a neutron-star merger that lit up the sky with gamma rays just moments after LIGO caught its gravitational wave signal. The results were staggering. After traveling 130 million light-years, the gravitational waves arrived at Earth less than 2 seconds before the gamma ray burst. Accounting for delays caused by the gamma rays interacting with interstellar gas, scientists calculated the speeds matched to within 1 part in a quadrillion. That's like timing 2 race cars crossing a finish line to within a millionth of a second over a distance of 1,000 miles. This wasn't just confirmation, it was a resounding validation of Einstein's century-old vision, closing one of the last major loopholes in testing general relativity. But why does gravity's speed matter beyond proving Einstein right? For starters, it shapes how we understand causality in the cosmos. If gravity moved faster than light, it could theoretically send signals backward in time, upending our concept of cause and effect. It also affects how galaxies form. The speed of gravity determines how quickly matter responds to changes in spacetime, influencing everything from star formation to the large-scale structure of the universe. And in extreme scenarios like black hole collisions, even tiny deviations in gravity's speed could alter how energy radiates away, changing the entire dynamics of these cosmic events. Perhaps most crucially, this discovery constrains alternative theories of gravity. Some modified gravity models designed to explain dark energy or dark matter predict subtle speed variations. The fact that gravitational waves and light arrived in lockstep rules out many of these alternatives, keeping Einstein's framework firmly in place. It's a reminder that the universe operates by strict, elegant rules, and thanks to gravitational waves, we're finally learning to measure them with the precision they deserve. Every new detection now serves as a speed test, reinforcing that gravity and light are cosmic partners, bound by the same universal limit. And as we peer deeper into the universe's violent corners, we're not just mapping collisions, we're conducting the most precise experiments in fundamental physics, with spacetime itself as our laboratory. When 2 black holes collide and merge, the violence doesn't end with the final crash, it echoes. Like a bell struck by a hammer, the newborn black hole vibrates, sending out gravitational waves in a rapidly fading sequence known as the ring-down signal. This cosmic reverberation is more than just an aftermath, it's a fingerprint encoding precise details about the black hole's mass, spin, and even the shape of its event horizon. And for physicists, it's one of the most powerful tools we have to test Einstein's theory of general relativity in the most extreme environment imaginable. Imagine the merger as a storm. The initial collision creates chaos, spacetime twists and contorts as the black holes spiral inward, releasing bursts of gravitational waves. But once they merge, the storm settles into a predictable pattern. The new black hole isn't perfectly smooth. It's misshapen, wobbling like a spinning top as it sheds its imperfections in the form of gravitational waves. These waves oscillate at specific frequencies, fading exponentially as the black hole settles into equilibrium. The pattern of this decay is what scientists call the ring-down, and it's as unique as a voice print. Here's where things get even more fascinating. According to the no-hair theorem, a cornerstone of general relativity, a black hole can be entirely described by just 3 properties: mass, spin, and electric charge. In other words, no matter how complex the objects were before merging, the resulting black hole should be bald, with all other details radiated away in gravitational waves during the ring-down. This means that by carefully analyzing the frequencies and decay rates of the ring-down signal, scientists can check whether the newborn black hole obeys Einstein's predictions or if there's hidden complexity hinting at new physics. The first clear detection of a ring down came from that historic 2015 black hole merger. As the waves faded, researchers isolated the distinct tones, like listening to the hum of a wine glass after it's tapped. The frequencies matched perfectly with what general relativity predicts for a black hole of that mass and spin, providing striking confirmation of the no-hair theorem. But with more detections, subtle deviations could emerge. Some theories of quantum gravity or exotic matter suggest black holes might have hidden hair, tiny deformations or extra quantum properties that would slightly alter the ring down. Every new merger sharpens our ability to probe these possibilities. Future detectors, like the space-based LISA observatory, will catch ring-down signals with even greater precision, potentially revealing whether black holes truly are as simple as Einstein thought or if they guard deeper secrets. It's like tuning into the universe's most precise tuning fork, one that doesn't just sound a note, but tells us how space-time itself behaves under the most extreme conditions. And with each ring down we analyze, we're not just studying black holes, we're stress-testing the very laws of physics. Think of the universe as a vast ocean, with gravitational waves rippling through space-time like perpetual waves. Now imagine trying to hear every single drop of rain hitting that ocean at once, an indistinguishable hum of countless collisions echoing from every direction. That's the gravitational wave background, a faint, all-pervasive murmur created by the overlapping signals of every black hole and neutron star merger that's ever happened in the cosmos. Unlike the sharp bursts we detect from individual collisions, this is a collective whisper, a cosmic static holding clues to the universe's most turbulent eras. For decades, scientists theorized this background must exist, but catching it seemed impossible. How do you isolate a hum when every detector on Earth is flooded with local noise, from seismic rumbles to passing trucks? The breakthrough came when researchers realized they didn't need to identify individual waves. Instead, they could search for statistical correlations in the data. Tiny patterns suggesting dozens of overlapping signals were shifting LIGO laser beams in sync. It's like listening for a distant choir when you can't pick out any single voice, but the combined harmony still resonates. The first tantalizing hints emerged in 2021 when an international team analyzed years of LIGO and Virgo data. They found a low-frequency hum consistent with predictions, likely the cumulative roar of millions of black hole mergers across cosmic history. But the real excitement lies in what this background could reveal. The amplitude and frequency spectrum of this static aren't random. They encode a timeline of the universe's merger rate, stretching back to when galaxies were just assembling. A louder hum at certain frequencies might hint at an era when black holes formed more prolifically, perhaps from primordial density fluctuations or exotic early universe physics. One provocative possibility is that this background hides traces of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. These ultra-thin, ultra-dense filaments would writhe and snap, sending shockwaves through spacetime. Their unique gravitational wave signature would stand out in the stochastic noise, offering proof of physics beyond the standard model. Alternatively, an unexpectedly strong signal could point to population Roman 3 stars, the universe's first generation of supermassive stars whose deaths might have seeded countless black holes we've never seen directly. The hunt is now accelerating with next-generation detectors. Projects like the Cosmic Explorer and Einstein telescope will have sensitivities tuned specifically to this background, while space-based observatories like LISA will probe lower frequencies, capturing mergers from supermassive black holes that predate galaxies. Together, they'll turn this cosmic static into a symphony, each frequency band revealing a different movement in the universe's violent history. What makes this search so revolutionary is its scale. Individual gravitational wave events are like snapshots, single frames in a cosmic film. The stochastic background is the entire movie playing all at once. By learning to decode it, we're not just studying black holes or neutron stars, we're reconstructing the universe's autobiography, written in vibrations too faint to hear until now. Among all the black holes detected through gravitational waves, a few stand out not for their size, but for their impossible origins. Take the 1.9 solar mass object that merged with a 23 solar mass black hole in 2019. On paper, it shouldn't exist. Conventional astrophysics says stars can't collapse into black holes that small, yet there it was, clear as day in the data. This cosmic oddball reignited one of astrophysics' most tantalizing ideas. What if some black holes weren't born from dying stars at all, but are relics of the Big Bang itself, leftover knots of spacetime forged in the universe's violent infancy? Primordial black holes are a radical alternative to the stellar collapse model. Picture the first fraction of a second after the Big Bang, when the cosmos was a seething, ultra-dense soup. Tiny fluctuations in density could have created pockets so compressed they collapsed directly into black holes, some as small as an atom, others as massive as a star. Unlike their stellar counterparts, these wouldn't need stars to die. They'd be cosmic artifacts drifting through the universe for billions of years before we detect their mergers. The implications are staggering. If even a handful of LIGO detections are primordial, it would mean the universe has been hiding an invisible population of black holes since the beginning. So where's the evidence that 1.9 solar mass object is a prime candidate? Stars can't realistically form black holes below about 5 solar masses. They'd stabilize as neutron stars instead. Yet multiple gravitational wave events now feature suspiciously light partners defying conventional models. Even more telling is the spin distribution. Primordial black holes, having never been part of binary star systems, would often have slow, random spins, a pattern LIGO has observed in several mergers. Combine that with the sheer number of detections in unlikely mass ranges, and the case grows stronger. But controversy looms. Critics argue these oddballs could still be explained by rare stellar processes, like neutron stars collapsing after accreting matter or exotic supernova. Others point to the lack of direct electromagnetic signatures. Primordial black holes merging in empty space wouldn't produce the glowing debris we see in neutron star collisions. The debate hinges on statistics. As LIGO catalog grows, peculiar events that look like noise today might reveal a pattern tomorrow. The stakes couldn't be higher. If primordial black holes exist, they could solve multiple cosmic mysteries at once. Some might be the elusive dark matter that holds galaxies together, their collective gravity outweighing visible stars. Others could explain how supermassive black holes grew so quickly in the early universe, seeding galaxies before stars had time to form. Every new gravitational wave detection is a potential Rosetta Stone, decoding whether these ancient relics are hiding in plain sight, or if the universe is simply more inventive than we ever dreamed. Gravitational waves don't just confirm Einstein's general relativity, they put it on trial, probing the boundaries of where his century-old theory might break down. For decades, physicists have proposed alternative theories of gravity to explain cosmic mysteries like dark energy or dark matter. Some suggest gravity behaves differently at extreme scales, while others argue for hidden dimensions or particles that alter its fundamental nature. But how do you test ideas that diverge from Einstein's framework in ways too subtle to measure on Earth? Enter gravitational waves, the ultimate cosmic laboratory. Take massive gravity, for example, a theory proposing that gravitons, the hypothetical particles carrying gravity, have a tiny amount of mass. If true, this would mean gravitational waves wouldn't travel exactly at light speed, and their waveforms might distort over vast distances. When LIGO detected the neutron star merger in 2017, the near-simultaneous arrival of gravitational waves and gamma rays ruled out massive gravity with unprecedented precision. Any deviation from light speed would have delayed the signals by minutes or hours, yet they arrived within seconds, slamming the door on many versions of this theory. Then there's the wild idea of extra dimensions, hidden realms of space beyond the three we experience daily. Some theories, like brain-world scenarios, suggest gravity could leak into these dimensions, weakening its force over large scales. Gravitational waves offer a direct test. If extra dimensions exist, merging black holes might lose energy into them, subtly altering the wave's amplitude or frequency. So far, LIGO observations match Einstein's predictions flawlessly, leaving no room for energy loss into unseen dimensions, at least not at the scales these mergers probe. But perhaps the most intriguing tests involve scalar tensor theories, which propose an additional field coupling to gravity. These theories could explain dark energy's acceleration of the universe, but they also predict that neutron stars deform spacetime differently than black holes. Gravitational waves from neutron star mergers carry imprints of their tidal deformations, letting scientists compare them to black hole signals. Any discrepancy would hint at new physics. Yet again, the data aligns with general relativity, tightening the noose around many alternatives. What makes these tests so revolutionary is their sheer precision. Lab experiments can't recreate the warped spacetime near merging black holes, but nature does it for us with gravitational waves as the readout. Every merger is a stress test, pushing relativity to its limits and narrowing the playground for rival theories. Some alternatives still cling to life, tweaked to evade these constraints, but the message is clear. Einstein's framework has passed every gravitational wave challenge thrown at it so far. That doesn't mean the hunt is over. Future detectors like LISA or the Einstein telescope will catch mergers at even greater distances where subtle deviations might finally appear. Until then, gravitational waves stand as the universe's strictest referee, separating mathematical speculation from the laws that truly govern the cosmos. And with each collision detected, we're not just listening to spacetime's whispers, we're interrogating the foundations of reality itself. One of the most heated debates in modern cosmology revolves around a single number, the Hubble constant, which measures how fast the universe is expanding. For years, astronomers have been getting different answers depending on their method, creating what's known as the Hubble tension. Traditional techniques like tracking distant supernova or studying the cosmic microwave background disagree by just enough to keep scientists up at night. But now, gravitational waves from neutron star mergers are stepping in as a game-changing third measurement, one that could finally tip the scales in this cosmic mystery. Here's why neutron star collisions are such a big deal. When two neutron stars spiral together and merge, they don't just send out gravitational waves, they also produce a brilliant flash of light. That light lets astronomers pinpoint the host galaxy and measure its distance the old-fashioned way, using redshift. Meanwhile, the gravitational waves encode how far the merger was based on the strength of the signal. By comparing these two independent measurements, scientists can calculate the Hubble constant directly, without relying on the cosmic distance ladder or assumptions about the early universe. It's like having two separate measuring tapes, one for space and one for light, letting us cross-check the expansion rate in real time. The first breakthrough came with that landmark 2017 neutron star merger. By analyzing the gravitational waves and matching them to the observed light, researchers calculated a Hubble constant value that intriguingly fell between the two conflicting numbers from other methods. That alone was exciting, but the real power lies in statistics. A single event can't resolve the tension, but with enough mergers, the data might reveal which side is correct, or even hint at something deeper, like new physics altering the expansion rate over cosmic time. What makes this approach so compelling is its independence from other techniques. Traditional methods are like measuring the height of a tree by counting the ring's cosmic microwave background versus stepping back and using a ruler supernova. Neutron star mergers, they're more like dropping a drone from the top, an entirely new way to gauge the distance. And as LIGO and Virgo detect more of these collisions, the precision improves, potentially exposing flaws in our current models or validating one side of the debate. The stakes couldn't be higher. If the discrepancy holds, it might mean our understanding of dark energy is incomplete, or that something even stranger is at play, like an undiscovered particle influencing cosmic expansion. Gravitational waves are handing us a fresh lens to examine this puzzle, one violent merger at a time. And with each new detection, we're not just measuring the universe's growth, we're challenging the very foundations of cosmology itself. In the chaos of a neutron star collision, the universe briefly creates something extraordinary, a supermassive neutron star teetering on the edge of oblivion. These ultra-dense objects form in the aftermath of mergers, packing so much mass into such a small volume that they shouldn't exist at all. Unlike ordinary neutron stars, which stabilize at around 2 solar masses, supermassive stars tip the scales at nearly 3 times that. So heavy, they're moments away from collapsing into a black hole. Yet for a fleeting instant, they defy gravity's grip, spinning furiously and radiating gravitational waves like a cosmic distress signal before vanishing forever. What keeps these stars from collapsing immediately? It's all about spin. Like a figure skater pulling in their arms to accelerate, the merged object rotates at dizzying speeds up to 1,000 times per second. This rapid rotation generates an outward centrifugal force, temporarily counteracting the crushing weight of its own mass. But it's a losing battle. As the star sheds energy through gravitational waves and magnetic winds, it slows down, and within milliseconds to seconds, the inevitable happens: the star buckles, its core imploding into a black hole. That brief window of survival is a goldmine for physicists, offering a rare glimpse into how matter behaves under conditions so extreme they border on the impossible. The duration of this balancing act tells us everything. If a supermassive neutron star lasts longer than expected, it suggests the nuclear matter inside is stiffer, more resistant to compression than our models predict. Shorter survival times hint at softer interiors where quarks or other exotic particles might be swimming freely. The 2017 neutron star merger provided the first clues. The gravitational wave signal showed oscillations consistent with a supermassive star lasting tens of milliseconds before collapse. That tiny delay alone ruled out some theories about neutron star composition, tightening constraints on how matter behaves at densities 100 trillion times greater than steel. But here's the real kicker: these ephemeral objects might solve another cosmic puzzle: short gamma-ray bursts. Some scientists think the supermassive star's death throes, as it finally collapses into a black hole, could power these intense flashes of energy. The star's magnetic field, amplified during the merger, might snap like a rubber band at the moment of collapse, channeling jets of radiation at near light speed. If future gravitational wave detections catch a merger where the supermassive star's lifespan matches the timing of a gamma-ray burst, it would be the smoking gun linking these two phenomena together. Every millisecond a supermassive neutron star survives is a defiance of cosmic odds, and a laboratory for physics we can't recreate anywhere else. With each new merger detected, we're not just witnessing a collision, we're catching the universe in the act of stress testing its own laws, pushing matter to the brink just to see what happens. And in that fleeting moment before the final collapse, these unstable giants whisper secrets about the true nature of gravity, matter, and the fabric of space-time itself. Most black hole mergers unfold like a carefully choreographed dance, two massive objects spiraling toward each other in near-perfect circles, their orbits tightening as gravitational waves bleed away energy. But sometimes the cosmos throws a curveball. Hidden in LIGO data are rare, chaotic collisions where black holes didn't follow the script. Instead of smooth spirals, they hurtled toward each other on wildly eccentric paths, tracing out lopsided, egg-shaped orbits. These aren't just cosmic oddities, they're smoking guns pointing to the most violent and crowded neighborhoods in the universe, where black holes don't get the luxury of polite introductions. They're thrown together in gravitational chaos. What causes these erratic mergers? Picture a dense star cluster where thousands of stars and their black hole remnants are packed together like commuters in a crowded subway. In this gravitational mosh pit, close encounters fling black holes onto bizarre trajectories. Some might get yanked into binary pairs after a chaotic three-body interaction, leaving them orbiting in tight, elongated loops. Others could be captured mid-flight, like two bullets colliding in midair. Unlike the calm, circular mergers we often see, these chaotic pairings leave a distinct fingerprint in their gravitational waves, a telltale wobble in the signal revealing their reckless origins. One of the first confirmed eccentric mergers detected in 2019 was a head-turner. The gravitational wave signal showed unusual modulation, as if the black holes were staggering drunkenly toward their doom. By reconstructing their orbital paths, scientists realized these black holes weren't born as a cozy binary pair. They'd been thrust together late in life, likely in a globular cluster, an ancient, densely packed city of stars. The implications are staggering. If even a fraction of mergers are this chaotic, it means dense stellar environments are far more efficient at pairing black holes than we ever imagined. But here's where it gets even wilder. Some eccentric mergers might involve not just two, but three black holes, a scenario where a third object disrupts a binary pair, sending one black hole flying while the other two merge in a lopsided death spiral. Simulations suggest these three body tangles could explain some of the most extreme orbital eccentricities detected. Imagine the gravitational waves from such an event, a frenetic, stuttering signal full of sudden jerks and dips like a seismograph during an earthquake. These chaotic mergers don't just entertain theorists, they're reshaping our understanding of black hole demographics. The fact that eccentric orbits exist at all suggests dense star clusters are black hole factories, constantly recycling these dark giants through violent encounters. Over time, these environments could churn out mergers too massive to form from isolated binaries, solving the puzzle of how some black holes grow so large so fast. Every eccentric signal detected is a window into the universe's most raucous neighborhoods, where gravity doesn't play by the rules and where black holes don't so much dance as they brawl. When gravitational waves pass through space, they don't just stretch and squeeze it randomly. They do so in a very specific rhythmic pattern, like a cosmic heartbeat. These patterns, known as polarizations, are the fingerprints of how space-time itself deforms under the influence of gravity. General relativity predicts two distinct polarization modes for gravitational waves, the plus mode and the cross mode, named for the way they distort space as they travel. Picture a circle of floating marbles in empty space. A plus-polarized wave would squish the circle horizontally while stretching it vertically, then reverse the motion, like an accordion breathing in and out. The cross mode does the same thing, but rotated by 45 degrees, twisting space diagonally instead of straight across. These two modes together create the distinctive ripple effect that detectors like LIGO and Virgo are designed to catch. But here's where it gets fascinating. Not all theories of gravity predict the same polarization behavior. Some alternative models, like scalar tensor theories or massive gravity, suggest there could be up to 6 polarization modes, extra twists and turns in spacetime that general relativity doesn't account for. These theories often introduce additional fields or particles that interact with gravity, subtly altering how waves propagate. For example, a scalar polarization might cause space to expand or contract uniformly in all directions, like a balloon inflating and deflating, while vector modes could create spiraling distortions. If these extra polarizations existed, they'd leave a clear signature in gravitational wave data, a smoking gun for physics beyond Einstein. The first major test came with LIGO initial detections. By comparing the signals from multiple detectors spaced thousands of miles apart, scientists could analyze how the wave deformed space at each location. The result, the data matched general relativity's predictions with stunning precision, showing only the plus and cross modes at work. Alternative theories, in contrast, would have produced mismatches in how the waves arrived at each detector, distortions that simply weren't there. This was more than just a victory for Einstein. It ruled out entire classes of competing gravity models in one fell swoop. But the real knockout punch arrived with the neutron-star merger in 2017. Unlike black holes, neutron stars possess strong tidal forces that can, in some theories, excite additional polarizations. Yet once again, the gravitational waves bore no trace of anything beyond the classic plus and cross modes. Even as the stars stretched each other apart in their final moments, space-time obeyed relativity's strict rules, warping in precisely the ways Einstein's equations demanded. It's as if the universe itself were reminding us, for all its mysteries, gravity still plays by an elegant, predictable set of rules. Every new gravitational wave detection now serves as another test, another chance for exotic polarizations to reveal themselves. So far, they haven't, and that absence speaks volumes. The more we listen, the more it seems Einstein's vision of gravity, with its two simple polarizations, is the one the cosmos has chosen. But the hunt isn't over. Future detectors with even greater sensitivity might yet uncover subtle deviations, hints of something deeper lurking beneath the surface of relativity. Until then, the polarization of gravitational waves stands as one of the most precise validations of general relativity, and a silent sentinel, guarding the frontier between known physics and the mysteries still waiting to be heard. When black holes merge, the violence of their collision doesn't just produce gravitational waves, it can launch the resulting black hole across the galaxy like a cosmic cannonball. These so-called black hole kicks happen when the merger isn't perfectly symmetrical, causing gravitational waves to surge out unevenly. Like a rocket expelling exhaust in one direction, this lopsided energy release sends the newborn black hole recoiling at speeds up to 5 million miles per hour, fast enough to escape even the strongest galactic gravity. Take the case of one particularly dramatic merger detected by LIGO in 2019. The gravitational wave signal revealed subtle irregularities in its waveform, clues that the black holes hadn't collided head-on but had spun wildly off-axis before merging. The result, a kick so powerful, the final black hole rocketed away at nearly 3,000 kilometers per second, over 1% the speed of light. At that velocity, it wouldn't just drift through its host galaxy, it would leave it entirely, doomed to wander the void between galaxies forever. But how exactly does this happen? Imagine two black holes spiraling together, their spins misaligned like gears grinding against each other. As they merge, the violent churn of space-time flings gravitational waves more intensely in one direction than the other. Conservation of momentum demands a counterbalancing thrust, literally pushing the merged black hole in the opposite direction. The more asymmetric the merger, the harder the kick. Some simulations suggest that under the most extreme conditions, these recoils could even reach 10,000 kilometers per second, though we've yet to detect one quite that fast. These gravitational wave kick signatures are more than just cosmic curiosities, they're reshaping our understanding of how black holes influence galaxy evolution. A supermassive black hole ejected from a galaxy's center could disrupt star formation for eons, leaving behind a dark core with no gravitational anchor. Smaller runaway black holes, meanwhile, might explain mysterious hypervelocity stars hurtling through intergalactic space, their paths tracing the invisible wakes of these dark fugitives. The most thrilling part, every new gravitational wave detection could reveal another high-speed escape. Somewhere out there, black holes are being flung into the darkness, their gravitational wave farewell notes telling the story of their violent birth and their spectacular exit. The universe's greatest enigma, dark matter, has eluded every telescope and detector ever built. Yet hidden within the faint echoes of gravitational waves, scientists are now finding tantalizing clues that this invisible cosmic scaffolding might be intertwined with the most violent collisions in the cosmos. One provocative theory suggests that some gravitational wave signals could actually be the death throes of dark matter itself, not in the form of exotic particles, but as primordial black holes forged in the Big Bang's first chaotic moments. Imagine if dark matter isn't an undetectable particle at all, but a vast population of ancient black holes too small to form from dying stars. These primordial relics would be virtually invisible, no glowing gas to accrete, no companion stars to betray their presence, yet their collisions would shake spacetime just like ordinary black holes. When LIGO started detecting mergers with unexpectedly light or heavy black holes, it raised eyebrows. Could these oddballs be the missing dark matter astronomers have sought for decades? Simulations show that if just a fraction of dark matter consisted of primordial black holes between 1 and 100 solar masses, their merger rates would align strikingly with LIGO observations. But the plot thickens. Some gravitational wave events feature black holes spinning so slowly they resemble solitary wanderers rather than products of binary star systems, exactly what you'd expect from black holes born in the early universe's turbulence. Even more compelling are the mysterious gaps in the mass spectrum. LIGO has found black holes at 50 solar masses and at 5, but almost none in between, a pattern that mirrors predictions for primordial black holes formed during specific phases of the early cosmos. It's as if the universe left us a breadcrumb trail in gravitational waves, hinting at a shadow population hiding in plain sight. Not everyone's convinced, of course. Critics point to microlensing surveys that should have spotted swarms of primordial black holes bending starlight yet saw nothing. Others argue that too many primordial black holes would disrupt the delicate chemistry of the early universe, altering the cosmic microwave background in ways we don't observe. But here's where gravitational waves offer an edge. Unlike light-based searches, they're blind to a black hole's origins. A merger is a merger, whether the objects formed yesterday or 13 billion years ago. The most radical twist, some theorists propose dark matter could be even stranger. Not black holes, but exotic compact objects like boson stars or gravastars, hypothetical entities with no event horizon yet dense enough to mimic black holes in collisions. These would produce gravitational waves with subtle differences, like echoes in the ring-down signal or missing tidal effects in neutron star mergers. So far, no such anomalies have been confirmed, but future detectors could spot the telltale glitches that betray dark matter's true face. What's thrilling is that every new gravitational wave event is a potential Rosetta Stone, decoding not just black holes but the invisible architecture of the cosmos. Whether dark matter turns out to be primordial black holes, something even weirder, or neither, each collision peels back another layer of this cosmic whodunit. And with upgrades to LIGO and new observatories coming online, we might finally be closing in on the answer. Gravitational waves have already shattered our understanding of black holes and neutron stars, but hidden within their faint ripples might be something even more revolutionary, the first whispers of quantum gravity. For over a century, physicists have struggled to reconcile Einstein's theory of general relativity with the bizarre rules of quantum mechanics. The two frameworks describe the universe flawlessly in their own domains: relativity for the cosmic scale, quantum theory for the atomic. But they clash violently when pushed to extremes, like the warped spacetime near a black hole's singularity. Gravitational waves could finally bridge that divide, offering glimpses of spacetime's granular quantum nature etched into the signals from merging black holes. The key lies in the most chaotic moments of a merger, the final plunge, where spacetime churns like a boiling sea. In these extreme conditions, some theories predict that quantum effects might subtly distort gravitational waves, imprinting tiny anomalies on the signal. One possibility is quantum foam, a hypothetical texture of spacetime at scales a trillion times smaller than an atom. Like static on a radio signal, this foam could introduce faint noise or glitches in the gravitational waves as they propagate across the universe. Other models suggest quantum corrections might alter how black holes ring down after merging, producing deviations from the smooth decay predicted by classical relativity. So why haven't we spotted these quantum fingerprints yet? The challenge is one of scale. Quantum gravity effects are vanishingly small, buried under layers of astrophysical noise from the mergers themselves. Current detectors like LIGO are like trying to hear a whisper in a hurricane. They lack the precision to isolate these minuscule fluctuations, but future observatories could change everything. The space-based LISA mission, with its million-kilometer-long arms, will catch lower-frequency gravitational waves from supermassive black holes, where quantum effects might accumulate over longer timescales. Meanwhile, third-generation ground-based detectors like the Einstein telescope will achieve such sensitivity. They might hear the individual pops of spacetime quanta snapping into place during mergers. The most tantalizing hints so far come from unexpected correlations in LIGO data, statistical oddities that some theorists argue could be early signs of quantum spacetime. One analysis found faint, repeating patterns in the noise surrounding certain mergers, resembling the echoes predicted by models of quantum black holes. Skeptics counter that these could just be instrument artifacts or random fluctuations, but optimists note that as more events pile up, the patterns persist. It's like finding the same scribble in the margins of multiple manuscripts, maybe a coincidence, or maybe the start of a new alphabet. What makes this search so electrifying is the stakes. If gravitational waves reveal even a single definitive quantum gravity signature, it wouldn't just confirm a theory, it would redefine reality. We might learn that spacetime isn't smooth and continuous but pixelated like a cosmic mosaic. Or that black holes aren't pure gravity wells but leak information through quantum tunnels, resolving Stephen Hawking's famous paradox. Every new merger brings us closer to these answers, turning gravitational wave astronomy into the ultimate laboratory for probing the fabric of existence itself. The universe has been hiding its quantum secrets for 13 billion years, but now, for the first time, we're listening closely enough to hear them. Most black hole mergers involve just two players, but the cosmos has a flair for drama, and sometimes the dance floor gets crowded. Hidden in the flood of gravitational wave detections are a handful of events so bizarre, they hint at something far more chaotic. Not just binary black holes, but triple or even quadruple systems spiraling toward catastrophe together. These aren't just cosmic oddities, they're windows into the most violent social networks in the universe, where black holes don't pair off politely but collide in messy, multi-body brawls that rewrite the rules of gravitational engagement. Take the curious case of one detection in 2021, where the gravitational wave signal showed strange, irregular modulations like a record skipping mid-song. Unlike the clean, symmetric chirps of typical mergers, this one wobbled as if a third black hole was tugging on the system, warping its orbit. Simulations later confirmed the culprit, a hierarchical triple system where two tightly bound black holes orbited a third, more distant companion. As the inner pair spiraled inward and merged, their gravitational waves carried echoes of the outer black hole's influence, a subtle but unmistakable fingerprint of cosmic crowd dynamics. How do these chaotic systems even form? Picture the densest star clusters where black holes sink to the center like marbles in a bowl, jostling for dominance. In these gravitational free-for-alls, close encounters can fling lone black holes into existing binaries, creating unstable trios. Some might stabilize for eons, while others, triggered by gravitational kicks from passing stars, collapse into a frenzy of mergers. The math is mind-bending. These systems evolve through a process called the Kozyledov mechanism, where the outer object's gravity stretches the inner binary's orbit into extreme ellipses, driving them to collide faster than they would in isolation. But the real shocker is what these systems imply about cosmic history. If triple black hole mergers are even slightly common, they could solve the mystery of how supermassive black holes grew so big so quickly in the early universe. Hierarchical mergers where one collision begets a larger black hole, which then merges again, might happen far more efficiently in these crowded environments. Imagine a galactic mosh pit where black holes pair up, merge, and immediately find new partners, rapidly bulking up like cosmic bodybuilders. Some simulations suggest this could produce black holes hundreds of times the Sun's mass by redshift 10, long before the universe had time to grow them through steady accretion. The wildest possibility, quadruple systems. While none have been definitively detected yet, theorists argue they must exist in the most packed stellar nurseries. Picture two binary black holes orbiting each other, their dance gradually decaying until all four objects plunge into a chaotic, almost unimaginable collision. The gravitational waves from such an event wouldn't just chirp, they'd scream, a cacophony of space-time ripples encoding the most violent party in the cosmos. Every multi-black hole detection peels back another layer of complexity in how these dark giants shape their surroundings. They're not just solitary predators or tidy pairs, they're social creatures, thriving in chaos, and their mergers might be the key to understanding how galaxies assemble their darkest, most massive hearts. With each new gravitational wave we catch, we're not just listening to the universe, we're eavesdropping on its most epic bar fights. When neutron stars collide, their surfaces aren't just smooth, featureless spheres. They're craggy, dynamic landscapes scarred by quantum-scale mountains and deep fractures. Gravitational waves from these mergers carry fingerprints of these imperfections, revealing how the neutron star's crust, a brittle, crystalline layer floating atop a sea of superfluid neutrons, behaves under unimaginable stress. Think of it like listening to a bell ringing after it's been struck. The sound isn't just a pure tone, it's laced with overtones and harmonics that betray every crack and flaw in the metal. Gravitational waves work the same way, encoding the secrets of neutron star crusts in their ripples. These cosmic mountains aren't like anything on Earth. While Mount Everest rises about 9 kilometers above sea level, a neutron star's crust might host deformations just centimeters high. Yet because of the star's insane gravity, those tiny bumps weigh as much as entire mountain ranges. Even more bizarre, these imperfections aren't static. The crust is under constant strain, tugged by magnetic fields trillions of times stronger than Earth's and stressed by the rotation of the superfluid beneath it. When two neutron stars spiral toward collision, their crusts stretch and crack like tectonic plates in fast forward, sending tremors through space-time that gravitational wave detectors can potentially hear. The smoking gun for this drama comes from pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses. Occasionally, these pulsars glitch, suddenly speeding up their rotation. The leading explanation, starquakes. As the neutron star spins down over time, its rigid crust warps under the strain until snap-it fractures, causing the star's outer layers to shrink slightly and spin faster, like a figure skater pulling in their arms. Gravitational waves from mergers could confirm this by revealing similar crustal dynamics in real time. If the waveform shows high-frequency oscillations in the final seconds before collision, it might signal the crust shattering, sending seismic waves racing across the star's surface. What's truly groundbreaking is how this ties into the broader puzzle of neutron star matter. The crust isn't just a passive shell, it's a quantum mechanical wonderland where atomic nuclei are crushed into bizarre shapes nicknamed nuclear pasta. Under extreme pressure, these nuclei arrange themselves into layers, sheets, and even spirals, resembling lasagna, spaghetti, or waffles. When a merger's gravitational waves distort these structures, they leave subtle imprints in the signal, like a seismograph recording an earthquake. By decoding these tremors, scientists can infer the crust's breaking strength, its thickness, and even how it interacts with the star's magnetic field. The implications stretch far beyond neutron stars themselves. If crust fractures power pulsar glitches, they might also explain fast radio bursts, mysterious, millisecond-long blasts of radio waves that could be caused by crustal collapses. Even wilder, some theories suggest that mountains on neutron stars could be persistent enough to create continuous gravitational waves, a faint hum detectable by future observatories. Every merger we observe adds another piece to this puzzle, revealing how matter behaves under conditions so extreme they defy laboratory physics. What's thrilling is that we're not just passive observers anymore. Gravitational waves let us feel these cosmic quakes, listening as neutron stars crumble under their own gravity. With each new collision, we're not just mapping the surfaces of these strange objects, we're touching the fabric of reality itself, one seismic ripple at a time. Gravitational waves don't just reveal black holes and neutron stars, they could soon become time machines, carrying whispers from the universe's very first moments. While light from the early cosmos was trapped in a fog of plasma until 380,000 years after the Big Bang, gravitational waves slice through that opacity untouched, offering a direct line to events we've never witnessed, the violent phase transitions and space-time quaking ruptures that shaped reality in its first fleeting seconds. Future detectors like the space-based Laser Interferometer Space Antenna, or LISA, aim to catch these primordial ripples, turning the static of the cosmic microwave background into a high-definition movie of creation itself. Picture the universe a fraction of a second old, a seething, superheated cauldron where the fundamental forces hadn't yet settled into their modern forms. As the cosmos expanded and cooled, it underwent dramatic phase transitions like steam condensing into water. But here, the steam was the unified electroweak force splitting into electromagnetism and the weak nuclear force, and the condensation released enough energy to send shockwaves through spacetime. These vibrations would now linger as a stochastic background of ultra-low-frequency gravitational waves, a fossil imprint of physics at energies 1 trillion times beyond what particle colliders can reach. LISA million-kilometer long arms will tune into these frequencies, decoding how and when these cosmic reorganizations unfolded. Even more tantalizing are cosmic strings, hypothetical defects in spacetime, thinner than an atom but stretching across the universe, left over from the Big Bang's cooling. Think of them as cracks in cosmic ice, vibrating as the universe expanded. If they exist, their oscillations would emit gravitational waves with a unique, comb-like spectrum of frequencies. A single string snapping could unleash a burst detectable across billions of years, a direct probe of quantum fields in the infant cosmos. Some theories suggest these strings might even form loops that collapse into primordial black holes, tying together two of astrophysics' greatest mysteries, dark matter and quantum gravity, in one audacious framework. The challenge is separating this primordial static from the cacophony of later mergers. But here's the genius: unlike black hole collisions, which produce transient chirps, phase transitions and cosmic strings create continuous or repeating signals with distinct mathematical signatures. It's the difference between hearing a single gunshot and recognizing the hum of a power plant. One is localized, the other pervasive. By mapping these patterns, scientists could pinpoint exactly when symmetry broke in the early universe, testing theories like grand unification or supersymmetry that predict specific transition temperatures. What's at stake isn't just a clearer history of the Big Bang. It's the potential to witness physics beyond the standard model. Current particle accelerators can't recreate the energies of the universe's first trillionth of a second, but gravitational waves from that era are already washing over us, waiting to be decoded. With each new detector, we're not just building better telescopes, we're assembling a time machine, one that might soon tune into the birth pangs of spacetime itself. Black holes are supposed to be the universe's simplest objects defined entirely by their mass, spin, and electric charge, with no other distinguishing features. This elegant idea, known as the no-hair theorem, is a cornerstone of general relativity. Yet lurking in the faint echoes of gravitational waves, scientists are now hunting for something far more scandalous: evidence that black holes might actually have hair, subtle deformations, or hidden structures near their event horizons that betray the presence of new physics or exotic matter. If found, these anomalies could crack open Einstein's theory, revealing layers of complexity we never imagined. The prime suspect in this cosmic investigation is the Kerr black hole, the theoretical ideal described by general relativity, with a perfectly smooth event horizon shaped only by rotation. According to the no-hair theorem, any bumps, wrinkles, or external fields should be rapidly radiated away as gravitational waves, leaving behind nothing but this flawless mathematical abstraction. But what if reality isn't so tidy? Some alternative theories of gravity, like scalar tensor models or theories involving extra dimensions, predict that black holes could retain faint imprints of their formation or surrounding environment. These hairs might take the form of external scalar fields, quantum corrections to spacetime, or even dark matter halos clinging to the event horizon. Gravitational waves provide the ultimate test. When black holes merge, the ring-down phase, the final fading vibrations of the newly formed black hole, acts like a cosmic fingerprint. Any deviations from the clean, predictable tones of a Kerr black hole could signal the presence of hair. For instance, certain exotic compact objects, hypothetical alternatives to black holes like boson stars or gravastars, would produce gravitational wave echoes, faint repetitions of the main signal caused by reflections near a quantum-structured horizon. These echoes, if detected, would be the smoking gun of physics beyond general relativity. So far, LIGO observations have overwhelmingly supported the no-hair theorem, with ring-down signals matching Kerr predictions to astonishing precision. But the hunt is far from over. Future detectors like the Einstein telescope or space-based observatories like LISA will scrutinize these signals with even greater sensitivity, searching for anomalies buried in the noise. Some theorists argue that primordial black holes, those born in the early universe's chaos, might be the most likely candidates to exhibit hair, their horizons potentially altered by quantum effects or interactions with exotic fields that no longer exist today. The implications of finding black hole hair would be revolutionary. It could mean that event horizons aren't the perfect one-way barriers we thought, but porous membranes leaking quantum information. It might hint at hidden symmetries in gravity or even provide clues about the nature of dark energy. Every new gravitational wave detection sharpens this search, turning black hole mergers into the most stringent tests of relativity we've ever devised. And if even one black hole out there refuses to follow the rules, it won't just change how we see these cosmic enigmas, it'll rewrite the laws that govern them. Einstein's theory of relativity gave us an astonishing prediction. Not only does gravity bend light, but it can also warp gravitational waves, creating cosmic echoes of the same collision. This phenomenon, called gravitational wave lensing, occurs when the fabric of spacetime itself acts like a giant magnifying glass. Imagine two black holes merging billions of light years away. If their gravitational waves pass near a massive galaxy or cluster on their way to Earth, the intervening gravity can split the signal into multiple copies, some arriving earlier, some later, like a symphony playing the same note at staggered intervals. The first hints of this came in 2020 when researchers noticed something peculiar in LIGO data, a suspiciously similar gravitational wave signal appearing twice in the same detector run. At first glance, it looked like a glitch, a technical artifact, but the waveform's near-perfect match suggested something far more intriguing. The team realized they might be witnessing lensed gravitational waves where a foreground galaxy cluster had bent spacetime so dramatically that it created two separate paths for the waves to travel. One signal took the direct route, the other swung around the cluster, arriving milliseconds later like an echo. What makes this effect so powerful isn't just its novelty, it's its potential to unmask the universe's darkest secrets. Unlike light, which scatters or absorbs when passing through dust or gas, gravitational waves barrel through everything untouched, making them ideal probes for mapping invisible mass. When a lensed wave splits, the time delay between copies and their relative strengths encode precise details about the lensing object's mass distribution, including its dark matter halo. It's like cosmic tomography. By analyzing the distortions in the signal, scientists can reconstruct the hidden scaffolding of galaxies in 3 dimensions, even spotting dark matter clumps too diffuse to detect any other way. One groundbreaking application involves empty lensing regions, areas where traditional light-based observations see nothing, but gravitational waves reveal subtle deflections. These ghostly distortions could point to rogue dark matter halos drifting between galaxies or even primordial black holes weaving through intergalactic space. Future detectors like the Einstein telescope will catch lensed waves routinely, turning each event into a precision measurement of cosmic structure. In essence, gravitational wave lensing doesn't just let us hear the universe, it lets us X-ray it, revealing the bones beneath its luminous skin, the most tantalizing possibility. Catching a wave lensed by an entire cosmic superstructure, a filament of the cosmic web, the vast network of dark matter connecting galaxies. These threads are so tenuous they're nearly invisible to traditional surveys. But a gravitational wave passing through one would stretch and split in telltale ways, offering our first direct map of the universe's largest scale architecture. With enough detections, we might finally understand how dark matter shapes the cosmos from the shadows, one lensed ripple at a time. While ground-based detectors like LIGO have revolutionized our ability to hear the high-pitched chirps of stellar mass black holes, they're deaf to the universe's deepest bass notes, the ultra-low frequency rumbles emitted by supermassive black holes millions of times heavier than our Sun. These cosmic giants don't merge with a snap, but with a drawn-out crescendo, their gravitational waves oscillating over years or even decades at frequencies too low for Earth-bound instruments to catch. That's where the Laser Interferometer Space Antenna, or LISA, comes in. A fleet of 3 spacecraft set to launch in the 2030s, forming a triangular gravitational wave detector with arms 2.5 million kilometers long. Unlike LIGO kilometer-scale tunnels, LISA will float in space, precisely tracking the distance between free-falling test masses using lasers. This staggering scale lets it tune into gravitational waves with wavelengths far longer than any earthly detector could measure. Frequencies between 0.0001 and 0.1 Hz, the sweet spot for supermassive black hole mergers. Imagine listening to an orchestra where LIGO catches the piccolos and violins, while LISA hears the tubas and double basses, revealing a hidden layer of cosmic music. The science this unlocks is monumental. Supermassive black hole binaries slowly spiraling toward collision at the hearts of merging galaxies will finally become audible. These systems take millions of years to coalesce, emitting gravitational waves the entire time. By tracking their gradual in-spiral, LISA could pinpoint exactly when and where galaxies will collide, giving astronomers a roadmap to the universe's most dramatic restructuring events. Even more thrilling, LISA might catch the moment these titans finally merge, warping spacetime so violently that the recoil kicks the resulting black hole clear out of its host galaxy, an event that would reshape an entire corner of the cosmos. But LISA's reach extends beyond black holes. It could detect the murmurs of millions of compact binaries in our galaxy, white dwarfs and neutron stars whirling around each other, mapping the Milky Way's hidden population in gravitational waves rather than light. It might even hear the relic rumble of cosmic strings snapping in the early universe or the ripples from phase transitions moments after the Big Bang. This isn't just a new telescope, it's a time machine tuned to frequencies we've never been able to access before, promising to rewrite our understanding of how the universe's largest structures grow and evolve. The most profound revelation might come from watching how gravitational waves change as they traverse the expanding universe. Unlike light, which redshifts as space stretches, gravitational waves could carry subtle imprints of how spacetime itself warps over cosmic distances, offering an entirely new way to measure dark energy's acceleration of the cosmos. With each passing year, LISA will compile a symphony of low-frequency signals, transforming gravitational wave astronomy from snapshots of violent collisions into a continuous, dynamic portrait of the universe's hidden vibrations. What's astonishing is that these waves are already washing over us, ripples from mergers so vast, they make LIGO detections look like whispers in a hurricane. We've just been waiting for the right instrument to hear them. When LISA finally launches, it won't just expand our cosmic hearing range, it'll open a portal to the universe's most majestic and slow-motion cataclysms, revealing a side of reality we've never been able to perceive until now. What if some of the signals we've labeled as black holes or neutron stars are actually something far stranger, objects so exotic they defy the very laws of physics as we know them? Hidden in the gravitational wave data could be whispers of theoretical anomalies like gravastars or boson stars, cosmic oddities that challenge everything we thought we understood about matter under extreme conditions. These aren't just alternate versions of black holes, they're radical departures from reality with structures so bizarre, they make the event horizon of a black hole seem mundane by comparison. Take gravastars, for example. Imagine a black hole's crushing gravity, but instead of collapsing into a singularity, the star's core is filled with a mysterious form of dark energy, creating a bubble of repulsive force that halts the collapse at the last possible moment. What remains is an object with no true event horizon, just a thin, ultra-dense shell of matter hovering over a void, like a cosmic eggshell protecting an unfathomable interior. Gravitational waves from a gravastar merger would carry telltale deviations, echoes in the ring-down signal caused by waves bouncing off this phantom surface instead of vanishing into nothingness. It's as if spacetime itself were ringing with a faint double beat, a signature no black hole could ever produce. Then there are boson stars, hypothetical objects made not of atoms, but of ultralight subatomic particles bound together by quantum forces. Unlike neutron stars, which are packed with protons and neutrons, boson stars would be more like gigantic, fuzzy quantum clouds, their matter spread out in a diffuse halo rather than a solid surface. When two boson stars collide, their gravitational waves would lack the sharp, violent chirp of a black hole merger. Instead, the signal would ripple outward like a pebble dropped into syrup, slower, smoother, and with subtle interference patterns betraying their quantum nature. Why haven't we spotted these exotics yet? The challenge lies in their subtlety. Current detectors like LIGO are tuned to find textbook black holes and neutron stars. Exotic signals might be hiding in plain sight, dismissed as noise or glitches. But future observatories like the Einstein telescope will have the precision to catch these anomalies. A single unambiguous detection would rewrite astrophysics overnight, proving that matter can stabilize itself against collapse in ways Einstein never envisioned. The real mind bender, some theories suggest these objects could be dark matter in disguise, hidden not in tiny particles, but in macroscopic structures lurking undetected across the cosmos. If gravastars or boson stars exist, they might solve two mysteries at once: the nature of compact objects and the identity of dark matter itself. Every gravitational wave we analyze now isn't just a ripple in space-time. It's a potential message from a universe far stranger than we've dared to imagine. Among the most tantalizing what-ifs in modern physics are cosmic strings' mythical defects in spacetime so dense, a single strand thinner than an atom could stretch across the universe, weighing more than entire galaxies. These hypothetical relics, theorized to have formed during the universe's first chaotic moments after the Big Bang, would be like cracks frozen into the fabric of reality itself. And while they've never been directly observed, gravitational waves might finally expose their existence by capturing the spacetime tremors they'd produce when snapping, vibrating, or intersecting. Picture the early universe as molten glass cooling rapidly. As it solidifies, tension creates microscopic fractures, imperfections locked into its structure. Cosmic strings would operate on a vastly grander scale, born when fundamental forces separated during phase transitions in the newborn cosmos. Unlike black holes, which warp spacetime into deep wells, strings would be one-dimensional flaws, concentrating unimaginable mass into infinitely thin filaments. Their gravitational influence would be bizarre. Anything passing near one would experience double vision, as the string's spacetime distortion creates twin images of background objects, like light bending around a razor's edge. But how would gravitational waves reveal these ghosts? A vibrating or snapping cosmic string would unleash bursts of gravitational radiation with a unique fingerprint, sharp, cuspy waveforms unlike the smooth chirps of black hole mergers. The most dramatic events would occur when two strings cross, slicing through each other and forming closed loops that oscillate wildly before vanishing in a puff of gravitational waves. These loops could persist for billions of years, acting like cosmic guitar strings, vibrating at harmonics determined by their length and emitting steady gravitational wave tones detectable by future observatories like LISA or the Einstein telescope. The smoking gun would be a statistical pattern in the gravitational wave background, a series of faint but consistent signals clustered at specific frequencies like comb teeth. Unlike random mergers, cosmic strings would produce a predictable, almost musical spectrum of vibrations across cosmic time. Some models even suggest these strings could seed galaxy formation, their immense gravity acting as scaffolding for matter to clump around in the early universe. What makes this search so electrifying is the sheer audacity of the implications. If cosmic strings exist, they'd be direct evidence of physics at energies a trillion times beyond what particle colliders can probe, a window into the universe's first trillionth of a second. They might even bridge the gap between quantum mechanics and gravity, as their behavior hinges on theories attempting to unify these fundamental forces. Every gravitational wave detector now scanning the skies isn't just listening for collisions, it's hunting for the echoes of spacetime's cracks, frozen in time since the dawn of existence. Neutron stars are cosmic laboratories of extreme physics, places where matter gets squeezed so tightly, it transforms into forms that defy imagination. For decades, theorists have argued over what happens inside these ultra-dense remnants of dead stars. Are they filled with free-floating quarks? Do their cores contain exotic particles like hyperons or strange matter? Or do neutrons themselves break down into some unknown state under the crushing pressure? Gravitational waves from neutron star mergers are finally providing answers, acting like interstellar X-rays that let us peer deep into the heart of these mysterious objects. The key lies in something called the equation of state, a mathematical description of how matter behaves under extreme densities. Think of it as the universe's recipe for neutron star material, dictating how stiff or squishy it is when squeezed. Different equations of state predict wildly different internal structures. Some models suggest soft, mushy cores that deform easily, while others propose rigid interiors that resist compression like cosmic diamond. When two neutron stars spiral toward collision, their gravitational waves carry imprints of these properties, especially in the final moments before impact. That groundbreaking 2017 merger delivered the first crucial clues. As the stars drew closer, their immense gravity stretched each other like taffy, creating tidal deformations visible in the gravitational wave signal. The degree of stretching revealed that neutron star matter is surprisingly stiff, far more resistant to compression than some theories predicted. This immediately ruled out several soft equation of state models, including ones where neutrons dissolve into a soup of free quarks at the core. The data suggested something more structured, perhaps layers of superfluid neutrons swirling around a solid crystalline crust, or even stranger phases of matter we've yet to name. But the real breakthrough came from combining gravitational waves with electromagnetic observations. When telescopes caught the afterglow of that merger, they independently estimated the star's masses and radii-critical data points that further constrained the equation of state. Like solving a cosmic Sudoku puzzle, each measurement crossed out impossible options, narrowing the field to a handful of viable models. One striking finding: neutron stars likely can't grow much larger than about 2.2 solar masses before collapsing into black holes, a limit that aligns with the stiffest remaining equations of state. Future detections are sharpening the picture even further. Some mergers show hints of rapid, high-frequency oscillations right before collision vibrations that could betray the presence of hyperons or other exotic particles in the core. Others lack the expected tidal deformations altogether, suggesting some neutron stars might be far smaller and denser than we thought. With each new event, we're not just testing theories, we're rewriting the textbook on how matter behaves when pushed beyond the limits of earthly physics. What makes this search so revolutionary is its directness. For the first time, we're not inferring neutron star interiors from distant pulsar glitches or theoretical calculations. We're feeling them deform in real time, listening as space-time itself shudders under their extreme conditions. Every merger peels back another layer, bringing us closer to answering one of physics' biggest questions: what happens to matter when you crush it beyond recognition? The answer might not just explain neutron stars, it could reveal entirely new states of matter hiding in plain sight, waiting to reshape our understanding of the universe's most fundamental building blocks. Black holes may be the universe's ultimate enigmas, but their spins tell a story, one written in the violent twists and turns of their birth. When two black holes spiral toward collision, their rotational axes don't just influence the merger's dynamics, they hold clues to how these cosmic giants formed in the first place. Gravitational waves capture this spin alignment with stunning precision, revealing whether the black holes were born together as a polite binary pair or thrown together in a chaotic cosmic encounter. And what we've learned so far has turned our expectations upside down. Take the case of a merger detected by LIGO in 2019, where the black hole's spins were dramatically misaligned, tilting at odd angles like a pair of tops wobbling wildly before crashing. This wasn't the orderly dance of a long-established binary system. It was the signature of a messy rendezvous, likely in a dense star cluster where gravitational encounters flung black holes together haphazardly. Picture a crowded ballroom where partners don't find each other gracefully. They're shoved together mid-step, spinning unpredictably as they collide. These misaligned mergers are smoking guns, proving that black holes don't always form tidy pairs from twin stars. Sometimes they're strangers forced into a violent embrace by the universe's most chaotic environments. But spin alignments reveal more than just formation scenarios. They're also testing Einstein's theory in extreme regimes. General relativity predicts that as black holes inspiral, their spins should gradually align with their orbital motion due to frame dragging, an effect where rotating objects twist spacetime around them like honey stirred in a cup. When gravitational waves show spins defying this alignment, it could hint at new physics, perhaps extra dimensions or exotic matter warping spacetime in unexpected ways. So far, the data overwhelmingly supports relativity, but every misaligned merger sharpens the test, probing whether Einstein's rules hold even in gravity's most frenzied arena. The real surprise, some black holes spin so fast, they're nearly at the theoretical limit, rotating at close to the speed allowed before spacetime itself would rip apart. These extreme spinners likely grew through repeated mergers, each collision adding angular momentum like a cosmic pinwheel gathering speed. Others barely rotate at all, suggesting they formed from stars that collapsed quietly without the explosive kick of a supernova. Each spin measurement is a puzzle piece, reconstructing the black hole's life history from birth to collision. What's emerging is a universe far wilder than we imagined, one where black holes form not just in serene stellar nurseries but in gravitational mosh pits where spins tilt and sway like compass needles near a magnet. With each new detection, we're not just mapping collisions, we're reading the autobiographies of black holes written in the language of spacetime itself. Some of the most distant gravitational wave detections sound like whispers from the edge of time itself. Ripples emitted when the universe was less than half its current age, carrying clues about how the first black holes grew to such monstrous sizes so quickly. In 2021, LIGO and Virgo detected a merger caused by black holes weighing 85 and 66 times the mass of our Sun. But the real shock came when astronomers traced their origin, a cosmic collision that happened over 7 billion years ago when the universe was just a third as old as it is today. This wasn't just another black hole merger. It was a window into the universe's adolescent years, a time when galaxies were smaller, denser, and far more chaotic than they are now. What makes these high redshift mergers so revealing is how they challenge our understanding of early black hole formation. Traditional theories suggest supermassive black holes grew slowly, feeding on gas and smaller mergers over billions of years. But the sheer mass of these ancient black holes suggests some must have started big, collapsing directly from gigantic clouds of primordial gas or forming through rapid, repeated mergers in packed stellar nurseries. The gravitational wave signal from that 85 solar mass black hole, for instance, showed a spin rate incompatible with a single stellar collapse. Instead, it likely formed from earlier mergers, bulking up fast in a cosmic environment where black holes were packed like sardines. These distant detections also probe the early universe's chemical makeup. Back then, before generations of stars had fused heavier elements, the cosmos was dominated by hydrogen and helium, the perfect ingredients for forming massive, fast-burning stars that could collapse directly into hefty black holes. Some models suggest these pristine conditions birthed black holes tens or even hundreds of times the Sun's mass, creating ready-made seeds for today's supermassive giants. Every high redshift gravitational wave event helps refine these models, letting us test whether the early universe was truly a black hole factory or if other exotic processes were at play. But detecting these ancient ripples isn't easy. The farther a gravitational wave travels, the more its signal stretches and weakens, like a voice fading across a vast canyon. To catch the faintest whispers, scientists employ tricks like matched filtering, comparing the data against a library of theoretical waveforms to spot patterns invisible to the naked eye. Advanced detectors like LIGO upcoming upgrades and the Einstein telescope will push these limits even further, potentially uncovering mergers from the universe's first billion years, a time when the first galaxies were just flickering to life. What's breathtaking is how these signals bridge cosmic eras. A black hole merger detected today might carry echoes from a time before Earth existed, before the Milky Way took shape, even before most stars had ignited. These waves are literal time capsules carrying immutable records of the universe's most formative collisions. And as we tune into ever more distant events, we're not just expanding our map of the cosmos, we're rewinding its history, one cataclysmic merger at a time. Right now, gravitational wave detectors like LIGO and Virgo are the sharpest ears we've ever trained on the cosmos, but the next generation of observatories will make them sound like tin cans connected by string. Projects like the Einstein telescope and Cosmic Explorer aren't just incremental upgrades. They're quantum leaps in sensitivity, engineered to catch whispers from the farthest reaches of spacetime with such precision. They could transform gravitational wave astronomy from a niche field into a mainstream window on the universe. The Einstein telescope, slated to begin construction underground in Europe later this decade, is a beast of a machine. Unlike current L-shaped detectors, it will form a triangle with 10-kilometer long arms 3 times longer than LIGO, buried deep beneath the Earth to shield against seismic noise. But the real game changer is its cryogenically cooled mirrors and advanced quantum squeezing technology, which will reduce the random jitter of photons to near zero. This lets it detect gravitational waves at frequencies 10 times lower than LIGO can manage, tuning into the deepest bass notes of black hole mergers from the universe's earliest epochs. We're talking about catching collisions so ancient, the stars and galaxies we see today hadn't even formed yet. Meanwhile, across the Atlantic, Cosmic Explorer aims to push the high-frequency frontier. With 40-kilometer arms 4 times longer than LIGO, it'll spot neutron star mergers up to 10 times farther away. Picture this: where LIGO might hear a few dozen events per year, Cosmic Explorer could catch thousands, turning rare cosmic snapshots into a high-definition movie of the universe's most violent events. But the real magic happens when these two work together. The Einstein telescope's low-frequency prowess will act like a cosmic early warning system, sensing supermassive black holes spiraling toward collision years in advance, while Cosmic Explorer zooms in for the high-frequency finale. It's like having both a wide-angle lens and a telescopic zoom on the same camera. What could these next-gen detectors uncover? For starters, they might finally catch the elusive intermediate mass black holes between 100 and 100,000 solar masses, objects too small to power quasars but too big to form from stellar collapses. These missing links could reveal how supermassive black holes grew so quickly after the Big Bang. They could also spot the faint, continuous gravitational waves from solitary neutron stars with mountains on their surfaces, deformations just millimeters high but weighing more than Mount Everest. These steady hums, drowned out by noise in current detectors, might hold clues to the true nature of nuclear matter under crushing pressures, but the most thrilling possibility is the totally unexpected. With sensitivity this high, we're bound to stumble upon phenomena no one's even theorized yet. Perhaps gravitational waves from cosmic strings snapping, or the peculiar vibrations of exotic objects like quark stars or wormholes. Every time humanity has built a sharper tool to observe the cosmos, we've stumbled upon something revolutionary. Radio telescopes revealed pulsars, particle accelerators found the Higgs boson. These next-generation gravitational wave observatories won't just add to our knowledge, they'll rewrite the textbooks, uncovering a side of the universe we've never even dreamed of. The sheer volume of data will be staggering. Future detectors could spot mergers every hour, forcing scientists to develop AI systems to sift through the flood of signals in real time, flagging the weirdest ones for closer study. It's like going from watching a handful of fireworks to standing in the middle of a galaxy-sized display, with explosions popping off in every direction. And buried in that cacophony might be the answers to our biggest questions: how dark matter bends spacetime, whether black holes truly have no hair, or if gravity itself behaves differently at cosmic scales. What's clear is this: we're on the verge of turning gravitational wave astronomy from a novelty into a fundamental pillar of how we explore the universe. Just as the Hubble Space Telescope transformed our view of the cosmos in visible light, these next-generation detectors will open an entirely new spectrum of observation, one where spacetime itself is the messenger. And when they finally switch on, we won't just be listening to the universe, we'll be decoding its deepest, most hidden rhythms for the very first time. Gravitational waves have done more than just confirm Einstein's century-old predictions. They've flung open a door to an entirely new way of exploring the universe. These 30 groundbreaking discoveries have rewritten astrophysics textbooks, turning what was once theoretical speculation into concrete, earth-shaking reality. From the first detection of colliding black holes to the haunting whispers of the gravitational wave background, each ripple in space-time has peeled back another layer of cosmic mystery, revealing a universe far more dynamic and violent than we ever imagined. Think about how much has changed in less than a decade. Before 2015, black holes were silent giants, their collisions invisible to our telescopes. Now, we've not only heard them merge but measured their spins, their masses, even the recoil kicks that send them fleeing across galaxies. We've caught neutron stars ripping each other apart, forging gold in cosmic kilns and answering questions about gamma-ray bursts that puzzled scientists for generations. We've probed the fabric of spacetime itself, testing relativity with a precision Einstein himself would have marveled at, and we've done it all by listening to the universe's faintest vibrations. But this is just the beginning. The next era of gravitational wave astronomy promises even greater revelations. Future detectors could uncover the fingerprints of dark matter hidden in exotic mergers or catch the echoes of cosmic strings snapping in the early universe. Space-based observatories like LIGO will tune into the low-frequency hum of supermassive black holes, tracing how galaxies merge and grow over cosmic time. We might even stumble upon something entirely unexpected, a signal that defies all current theories, hinting at dimensions beyond our own or new states of matter lurking in the hearts of neutron stars. What's most exciting is that this revolution isn't confined to academic journals or elite research labs. Every new detection is a shared discovery, a moment where humanity collectively leans in and listens to the cosmos. Whether you're a scientist, a student, or simply someone who gazes up at the stars and wonders, gravitational waves invite you to be part of the story. They remind us that the universe isn't just out there, it's speaking to us if only we know how to listen. So stay curious. The next time you hear about a gravitational wave detection, remember, you're not just witnessing science history. You're hearing the universe reveal its secrets one ripple at a time, and who knows, the next big discovery might be the one that changes everything.